Hello everybody, thanks for tuning in. Today I just want to talk about one-dimensional uniform steady flow approximations and go over a few of the equations that we use to calculate one-dimensional uniform steady flow. So first off, we'll start off with St. Venant's equation, or set of equations, which is the conservation of momentum and the conservation of mass. The conservation of momentum, this equation can be derived from Navier-Stokes conservation of momentum equations. Within this derivation, we have a change of velocity with respect to time term, a change of velocity with respect to position term, pressure term, and this is going to equal gravity times the bed slope minus the friction slope. Within this equation, we can see that we have a one-dimensional approximation because we are only considering terms along the x direction, which the x direction will be along the bed slope downstream. Downstream is the positive direction. So now now that we know that we have one-dimensional flow, using the assumption of uniform flow, this is going to imply that any property, there's going to be no change in any of the properties with respect to the position. So the flow, area, velocity, Manning's N, all that is constant along our geometry. Excuse me. We are also going to assume steady state, which is going to imply any property with respect to time going to be zero, so no change in any property with respect to time. So going back to this momentum equation, this is going to leave this term 0, this term 0, and this term 0, rendering us with just this term, which is what we have here. Dividing out the g, we have the bed slope minus the friction slope, which is equal to 0. So what does this actually mean? Well, this means the slope of the energy gradient line is equal to the bed slope, where if we add over the friction slope to the other side, and we know the friction slope is equal to the head losses due to friction divided by the length of the section that we're analyzing, we can say that the friction slope will be equal to the bed slope, and all this is equal to the energy gradient line. And in other words, what this is saying is that the friction is going to be equal to gravity, which ultimately means the resisting force is equal to the driving force, and that we have no acceleration, and that our velocity is constant from one point to another. Then, using the conservation of mass, this is also part of the St. Venant's equation. We can see the change in area with respect to time plus the change in flow with respect to position. This is going to be 0 because of steady state, and this is going to be 0 due to uniform flow. So the flow is constant in the x direction. So from point 1 to point 2, since the flow is going to be constant, and we know that the area is constant, also with respect to position and time. We know that the area on this side is going to equal to the area at point 1, or the area at point 2 is going to equal to the area at point 1. We also know the velocity is constant. This is going to mean that, and if all that is the case, then our equivalent flow rates should be constant. Now, if we look at the conservation of momentum diagram, we have from point 1 to point 2, we have a pressure force driving and a pressure force resisting. Since the depth here and the depth here are equal, the hydrostatic force on this side and on this side will be equal. We also have a driving force due to gravity in terms of the bed slope. And then we also have a friction term in terms of tau. Then summing all the forces in the x, which will be equal to the conservation of momentum, we have which is beta times density times q times velocity. This is going to give you, or I guess one thing to know is that the momentum correction factor beta is going to be constant between both the sections, and that's because the beta is dependent on the velocity and area, and since those are constant, beta 1, beta 2 will be constant. We know q1, q2, q1 equals q2, v1 equals v2. We also know that the normal vector on point 1 is going in this direction, but the flow is going in the opposite direction. So that's going to imply that this term here is negative at point 1. The normal vector is in this direction. The velocity is also in that direction, which means this term here is positive. Now we know P1 equals P2. Those will cancel, and that will leave you with W sine alpha minus tau. This is going to imply that our driving force is equal to our resisting force, or in other words, our gravity is equal to friction, like we claimed earlier. So these are basically the main assumptions that are going to be governing the applicability of our one-dimensional uniform steady flow approximation equations, which first off we have Chezy's equation, which is Q equals area times C star times this business, where the R in this formula is the hydraulic radius, which I'll go over in a second. And then just some formulation of C star is basically just your velocity divided by your shear velocity. Your shear velocity is defined by this, and then your velocity is defined by this. And then if you divide out V by V star, we'll cancel out this V star, which will leave you with C star equal to this equation here, where this K value is just your effective roughness, which is basically like a sand grain roughness for your bed. And that's dependent on soil properties and all that nature. And then we have Manning's equation, which is basically just equal to Q equals phi divided by N times this business. Phi is equal to 1.0 for SI units and 1.46 for imperial. S is the bed slope, and N is Manning's N. This is going to be dependent on sort of like your what kind of bedding you're going to be seeing, whether it's on the bank full stage, whether it's you're actually flooding on your floodplains, and you might have some vegetation, and you might need to calculate a like a weighted average for your Manning's N, depending on the situation that you're trying to model. That's basically it for Manning's equation. And then hazen-williams is basically just a different formulation for C star that you would plug into Chezy's formula. And with that is just the A parameter and the M parameter. And one thing to note about these equations is that there's a certain range of R over K values where Manning's formula will converge with Chezy's formula. And there's a certain range of R over K values that hazen-williams formula will converge with Chezy's formula. And that's pretty much it. Thanks for watching, and I'll see you guys on the next video.